Hello, today's lab is going to be about the photoelectric effect. Now we know what this is. It was Einstein's discovery, well, he didn't really discover it, Einstein's explanation of why when you shine light on various metals, you can get a current. We're going to be doing this basically exactly, and we're going to use it to measure Planck's constant, that whole 6.626 times 10 to the negative 34th joule seconds. Now, the basis of this is we are going to fire photons out of this, and you can see what I mean. We're going to fire photons out of that into this chamber where there is a photodiode. Now, the photons we fire have an energy of hf, Planck's constant, times the frequency of the light that passes through. And the total energy will be nhf, the number of photons, times those values. What we're going to do is we are going to restrict the frequency of light going in by adding various filters. Now, the filters are measured by wavelength. For example, this red one is 635 nanometers. Keep in mind when you are doing this, you are going to need frequency in hertz. Now, I'm going to give you the values of these wavelengths in nanometers. So yeah, the first one is 635 nanometers. When you convert that to frequency, keep in mind that the frequency times wavelength is energy. However, you must work in meters, not nanometers, when you do that conversion. Now, what I'm going to do is I am going to put this red filter. What that does is it makes it so that only wavelength 635 nanometer light passes through. And then now that I have that light going, what I'm going to do is I am going to shine light inside. Now, as you can see, when I shine this light in, I am now getting a current. That current is 0.44, well, it's adjusting, as you can see, but it's slowly balancing out. But there is a current in microamps. It looks like about 0.460 microamps. What I'm going to do is I'm going to right now, that light is causing a circuit. I'm going to put a voltage pointing in the opposite direction. And I'm going to put a voltage pushing against that. And so what I would do is I will start giving it a voltage, a bigger and bigger voltage. And the voltage pushes against it. I'm going to push the voltage until the current turns into zero. A little too far. So right now my current is zero. My current is zero because I have a voltage pushing against it. Well, whatever voltage I pushed against, that is known as the stopping voltage. That is how much voltage I needed to stop it. And if I flip this dial, it'll give me that stopping voltage. Now that negative sign just means in the negative direction. You can ignore that when you're entering your data. But that right there is what you'll put for the voltage. Now this is another one of the ones where I am not going to give you the data. I am just going to expect you to watch the video. It will be a little long and I apologize. Now that we find that stopping voltage, I want you to find the energy that equivalent to that stopping voltage. To find the energy of the stopping voltage, it is going to be that value, 0.24 volts, times the charge of an electron. Now, I said you can ignore the negative. Really, you shouldn't ignore the negative. The charge of an electron is negative 1.6 times 10 negative 19, but the two negatives will cancel each other out. And so, for my 635 nanometer red, that is the stopping voltage. I'm going to put this back. I'm going to turn off my light. And I'm going to go to my next color. This next one is a yellow at 570 nanometers. And I'll turn my light back up. I will find the stopping voltage. And that is my stopping voltage. You'll note that I'm turning off the light between each one. That's a reason for that. If I was to have the light full blast without filter, it would probably overload the piece. This next one, it's much more yellow. This is 540 nanometers. Let's say close enough. That's my stopping voltage. That was the stopping voltage for yellow. We've done red, then orange, then yellow. Next, we did red, orange, yellow. It's kind of obvious what's next. Green. My green is 500 nanometers. And so there's my stopping voltage. And last, we're going to do blue. Blue is at 460 nanometers. Oop. Oh shit. I messed up. Luckily, I didn't destroy anything. And that's my stopping voltage for blue. So you can take those stopping voltages and put them in. And what you're going to do is you're going to find, for each wavelength, find what frequency it corresponds to. For each stopping voltage, find what energy that corresponds to. And since E equals HF, you'll plot the energy versus the frequency. And the slope of your graph should be H, Planck's constant. Good luck.